Morning, good afternoon, good evening, everyone across the world. Welcome to the ICANX Youth Talk today. Um, my name is my, my name is Haotian Chen. I'm from University of Glasgow, and I'm very pleased to
So
be.
Haotian, you didn't share the screen now. Yeah.
You see it now?
Yes.
Okay, I'm sorry. So again, welcome all of you coming to join today's webinar. My name is Haotian Chen from University of Glasgow. I'm very pleased to be the moderator of today's webinar. And today's webinar will cover the topic of advanced material and sensing technologies. And we are very honored to have three distinguished speakers from three continents. They are Dr. Haiyang Mao from the Chinese Academy of Science, Dr. Ying Zhu from the University of Technology, Sydney, and Dr. Rajeev Gupta from North Carolina State University. In the meanwhile, we also have two talented researchers as our panelists to join the discussion. They are Dr. Jiu Shuai Xu from TU Braunschweig and Dr. Jinchi Han from Peking University. Thank you all of you coming. So I hope that today's webinar will not provide you with a very most up-to-date research work, also give you some inspiration from the insightful discussion. So let me first introduce our first speaker. Dr. Haiyang Mao is currently a professor at Institute of Microelectronics of Chinese Academy of Science. She received her PhD degree in microelectronics and solid-state electronics from Peking University in 2011. Her research interests include MEMS devices and nanomaterial-based sensors. Professor Mao has published more than 70 peer-reviewed papers like advanced functional materials, small ACS sensor, etc., and contributed over 40 conference talks like IEEE MEMS, transducers, etc. Besides, she has applied for over 100 patents and authorized 45 patents. She has also developed several MEMS sensor products by focusing on the industrialization of MEMS sensors. She has produced tens of millions of sensor chips and modules, which have been widely used in fields of biomedical research, smart home, and industrial. So, welcome, Dr. Mao. Again, the stage is yours.
Haiyang, you mute. Okay.
Okay. Thank you, Dr. Chen, for your kind introduction, and thanks, Professor Alice Zhang, for your invitation. Hello, all. My name is Haiyang Mao from Institute of Microelectronics, Chinese Academy of Sciences. Today, my talk is about microsensors with nanoforests. Okay, here is the outline of this talk. In this talk, I will introduce the fabrication and the properties of the nanoforests, and then, based on the properties of the nanoforests, I will further introduce the two typical microsensors integrated with nanoforests. Sensors with the ability of information collection have been used almost everywhere in our daily lives. In recent years, with the rapid development of Internet of Things, automotive electronics, health electronics, and the artificial intelligence, sensors have become increasingly important as the key components in this system. With the expansion of sensor applications, there are requirements to improve sensor performance. Nanomaterials and nanostructures can bring higher performance to the sensors due to their unique properties such as small size effect and surface or interface effects. Currently, different nanomaterials and nanostructures have been integrated into different sensors. In this talk, I will introduce two types of typical sensors, namely the thermopile infrared sensors and the humidity sensors as examples, in which nanostructures are used. Forehead thermometers are widely used in daily lives for real-time body temperature detection. In such a handheld small device, the most central part is the thermopile sensor. Along with the ability of non-contact body temperature detection, such a sensor can also find applications in smart home, smartphones, industrial temperature measurement, automobile electronics, and also intelligent office equipment. Like all the other MEMS sensors, how to improve performance of thermopile infrared sensors is also an eternal topic. As the thermopile infrared, sorry. As the thermopile infrared sensor is a type of optical sensors. For an optical sensor, the improvement of its performance depends on the optimization of device structures on the one hand, and on the other hand, depends on the device's ability to absorb light, because there is direct relation between the performance and the device's ability of light absorption. Therefore, utilizing the high absorption property of nanostructures caused by the light trapping effect is another important way to improve device performance. At present, similar ideas have been applied to sensors with working in other wavelength bands, including the infrared sensors. Humidity sensor is another type of commonly used devices. In addition to the regular indoor or outdoor environmental monitoring, the humidity sensors have also been used in industrial production, agricultural planting, and others. In recent years, there have been new demands for the humidity sensors in respiratory detection, urine detection for all the baby diapers, human sweat detection, and also non-contact human-machine interaction. For humidity sensors, there are many working principles and different structures. The interdigital electrode capacitive structure is the most commonly used. The traditional interdigital electrode structure is prone to introducing parasitic capacitance from the substrate, which affects the measurement results of the sensors. In addition, the traditional humidity sensing materials such as PI photoresist may have low sensitivity because due to their insufficient hydrophilicity. At the same time, they have semi-closed nanostructures, therefore may lead to long-term absorption and desorption of water molecules. Therefore, the response time and the recovery time of the devices might be long. In response to these two issues, different nanomaterials with larger surface areas and improved hydrophilicity have been used to achieve higher detection sensitivity and faster response speed of the devices. For the nanostructures that can be integrated and applied in such MEMS sensors, their preparation processes can mainly be divided into two categories, serial and parallel approaches. Among the serial process technologies, although the serial process technologies can accurately control the size and the position of the nanostructures, they generally rely on high-end instruments and equipment, and the serial processing nature also lead to time-consuming and high-cost issues. On the other way, well as chemical synthesis grows and nanosphere lithography, metal-assisted chemical etching technologies, they can prepare nanostructures in parallel. However, they also face problems such as difficulty in large-scale batch control, incompatibility with CMOS processes, and the introduction of metal catalysts that may easily cause metal pollution in the device, which even may lead to short circuit of the devices. To sum up, these are the challenges of the current preparation processes. To solve these problems, we propose a new type of nanostructures, which we call nanoforests. And also we proposed a novel process to fabricate the nanoforests. In semiconductor technology, photoresist stripping using plasma is a commonly adopted dry process step. Generally, we believe that after a long period of photoresist stripping, the substrate surface should be quite clean and tiny. However, we found this kind of dotted and flocculent nanomaterial residues in our experiment. Based on this experimental phenomenon, we have undergone continuous process debugging and parameter adjustment to regulate the dotted and flocculent nanomaterials to form nanoforests. Currently, we have been able to fabricate nanoforests with different diameters, different heights, densities, and even different tilting angles. Here, we will use a video to demonstrate the fabrication process of the nanoforests. Firstly, the patterned polyimide photoresist is bombarded with an oxygen plasma to form fibrous nanostructures. The diameters of an individual nanofiber is about 10 to 15 nanometers. Furthermore, under the bombardment of argon plasma, fibrous nanostructures undergo reaggregation, forming pillar-like nanoforest substrate structures with larger diameters. And at this state, the diameter of an individual nanopillar is approximately 100 to 300 nanometers. Based on this process, we also deduced the preparation mechanism of these nanoforests. As we know, there's silane coupling agent existing in photoresist. Silane coupling agent has both organic and inorganic chemical bonds. Because of this structure features, there forms a complex in the photoresist through the silane coupling agent. Under the action of plasma bombardment, the organic chemical bonds in the complex is gradually opened and broken, and the physical bombardment of the plasma gradually breaks the inorganic chemical bonds in the lateral direction, leaving only those in the vertical direction, which initially appear as the dotted or flocculent nanomaterials, and then with their height gradually increased, ultimately show as the nanofiber forest standing upright on the substrate. Based on the above deduction, we propose a silane coupling agent-assisted plasma repolymerization technique to prepare diverse form nanoforests. So, from the preparation mechanism, it can be seen that the materials of the prepared nanoforest has been totally different from the original PI photoresist. After a lot of tests, at this time, we have known that the nanoforest are made of elements of silicon and oxygen, which is similar to silicon dioxide. Therefore, it can be further used as nanomasks for silicon substrate etching to transfer the nanoforest to the silicon substrate. So far, we have prepared diversible nanoforests based on such approach and the method. In this slide, we can see, in addition to the silicon-based nanoforest, we have also prepared the nanoforest of different metals, zinc oxide nanowires, gallium nitride, gallium oxide, aluminum, sapphire, and also quartz and the other materials. So far, this nanoforest has been used in different devices and have improved performance of these devices significantly. This is because the nanoforests have surprising properties in different aspects. And this is what we are going to discuss in the following part. As we know, silicon-based nanoforests exhibit excellent broadband and high absorption feature due to their surface effect, size effect, and light trapping effect. Such a structure is sometimes known as black silicon. However, restricted by the band gap width of the material, the absorption rate of the silicon nanoforest decreases significantly when the light wavelength is larger than 1.1 micron. In order to broaden the high absorption band, we propose a method to introduce the surface plasmon resonance into the system. So, to testify this idea, we used a transparent flexible substrate. We prepared the nanoforests on both sides of this substrate and introduced gold nanoparticles on the nanoforest with a thickness of about 30 nanometers. Firstly, as visible to the naked eyes, the flexible transparent substrate became a flexible ultra-black substrate. And within the wavelength range from 200 to 2400 nanometers. The average absorption increased from the initial 27% to the 92%, achieving a wide band high absorption. The wide band high absorption property of the nanoforest can be attributed to two effects. One is the light trapping effect of the nanoforest, since they have a large aspect ratio. The other is the hybrid surface plasmon resonance effect. The hybrid plasmon resonance effect mentioned here includes the localized surface plasmon resonance caused by the metal nanoparticles and the cavity mode resonance between the nanowires, and also the waveguide mode resonance inside the nanowires. Due to the different sizes, distribution, and the spacing of the metal nanoparticles and the nanowires, each size and distribution corresponds to a separate absorption peak. The coexistence and overlap of the multiple absorption peaks broadens the high absorption band, ultimately forming a wide wavelength band and high absorption. Since the nanoforests have no structural difference in the X and Y directions, the light absorption characteristics of the nanoforests are not sensitive to polarization. In addition, due to the large aspect ratio of the nanoforests, the light trapping effect is also insensitive to the angles of the incident light. From these two perspectives, we can say that the nanoforest is naturally a perfect light absorber. On the other hand, the nanoforests also have a high moisture absorption property. As we can see here, the nanoforests have a super large surface to volume ratio. Besides their inherent hydrophilic groups like hydroxyl groups make them super hydrophilic. Based on such nanoforest, self-driven surface microchannels with a relatively long driven distance can be formed. But of course, with surface modification with hydrophobic groups can regulate the wetting properties of their surfaces, even to reach a semi-wetting state and to present a super hydrophobic and highly adhesive surface. With such wetting properties, the nanoforest can be used as a humidity-sensitive material due to the large surface area, abundant hydrophilic groups on their surfaces. Under different humidity conditions, change in dielectric constant can be generated through the synergistic effect of chemical absorption and physical absorption. When a small amount of water molecules enter the nanoforests, the molecules are chemically absorbed to the functional groups to the surface through the hydrogen bond. In the process, the water molecules occupy the active sites on the surface one by one. With the increase of relative humidity, physical absorption can occur under the action of van der Waals force, forming a single layer of water molecules, and later will transist to a multi-layer water molecular film. On the other hand, because there are a large number of capillary pores with different sizes and shapes in the nanostructures and in between, according to Kelvin's theory, such structure will undergo capillary condensation under different humidity conditions. Smaller pores can undergo capillary condensation at a lower humidity, and as the relative humidity increases, capillary condensation also occurs in the larger pores. In addition, due to the one-dimensional order, the morphology distribution of the nanoforests, and due to their hydrophilicity, the condensed water molecules layer can transfer along the vertical structure downwards to the bottom of the nanoforests and converge at the metal electrode positions. Therefore, the effective dielectric constant further increases, which in turn enhances the sensitivity of the device. So, as the nanoforests have the aforementioned features, we further use them in different MEMS sensors. Here we are going to talk about two different types of sensors. So firstly, let's take a look at the thermopile infrared sensors. Thermopile infrared sensors are devices based on Seebeck effect by using thermocouples with different Seebeck coefficient. When the device absorbs infrared light and forms the temperature difference between the cold and hot ends of the thermocouples, a voltage will be formed at the cold ends of the device. Based on this working principle, and also by taking use of the isotherm distribution, we have constructed a MEMS thermopile infrared sensor. In such a sensor, double-layer polysilicon thermocouple structures and the thermoconductive electrical isolated structures are used. The use of the double-layer polysilicon thermocouples and the thermoconductive electrical isolated structures helps to reduce device size by 60%, reduce the cost by 50%, while maintaining the high performance of the devices. So based on this sensor, we have formed a lot of products, and our products have also met various standards and have obtained the CE certification, RoHS certification, and also passed the reliability testing, EMC testing, and performance testing. Due to the excellent device design and advanced technology research capabilities, the yield of the sensors reaches 98%, and the devices have been widely used in customers and products. By now, the shipment of the sensors and their modules has exceeded 30 million pieces. Here shows the applications of the devices in different temperature measurement products. So previously, we introduced our work in the research and development of conventional MEMS thermopile infrared sensor products. Further, we will integrate the Nanoforests onto the thermopile sensor by taking advantage of the wide band and high absorption of the Nanoforests. So the performance of the device is expected to be improved. This image shows the integration schematic diagram, and the Nanoforests are prepared only in the absorbers, of the device by using photolithography. This is the preparation process for the device with Nanoforests, where the Nanoforests are integrated after the product is processed, so it will not affect the original process flow, and will not affect the yield of the device, and also will not increase too much development cost to the products. The testing results show that the performance of the thermopile sensor integrated with the Nanoforests can be improved at least 35% in the infrared band, and even 3 to 5 times when the incident light is with short wavelength range. Recently, such a technology and such sensors have also been used in customers and products. Further, we also applied the new thermopile sensors in other devices, including the non-dispersive infrared gas sensors, the gas flow sensors, and Pirani gauge. As we can see here, the performance of these sensors has been greatly improved after the integration of Nanoforests in the thermopile sensors. So that's about the thermopile infrared sensors. Now let's look at the humidity sensors. In the previous slide, we've discussed the humidity sensitive mechanism of the Nanoforests. Based on this, we further designed a new type of MEMS humidity sensors. In this device, we simultaneously designed a sensing capacitor, reference capacitor. Here, the reference capacitor uses silicon nitride as is a dielectric material, and the sensing capacitor uses a Nanoforest as the humidity sensing material. With these two capacitors, the device utilizes differential output to eliminate parasitic capacitance, and utilizes the Nanoforest to improve detection sensitivity. At the same time, we also integrated a thermistor in the device to calibrate temperature drift, and also a microheater to further accelerate the response speed. The fabrication process of the device is quite simple, which requires only 5 layers of photolithography. From the SEM images, it can be seen the Nanoforests are standing upright between the electrodes. After simple packaging, we tested and calibrated the performance of the device. In terms of sensitivity, this device has increased by 8 times when compared to the original PI-based device with the same structure and the same dimensions. Due to the combined effect of the nanoforests and the microheater, the response time of the device can be shortened from 11 seconds to 5 seconds. So based on such a humidity sensor, we further developed a module to monitor respiratory status or a human being, and also developed a machine learning algorithm to for the recognition of human motion states. At present, the comprehensive testing accuracy of 9 motion status has reached 91.4%. In addition, as the preparation of the nanoforest is not limited by the substrate material, we also patented the nanoforest on a flexible substrate and constructed a nanoforest-based flexible humidity sensor and its corresponding array devices. It can be seen here that our method can achieve wafer-level preparation. From the testing results, the nanoforest-based flexible humidity sensor has excellent repeatability, bending stability, and long-term stability. At the same time, its response time is much shorter than the similar competitors, and its sensitivity is higher. With such a flexible device, we realized the non-contact switch control of electrical quantities. At the same time, based on the sensor array, we also realized the real-time monitoring of hand gestures as well as the hand movement trajectories. Based on this, we also achieved the control of other quantities like the toy trucks. Okay, finally, here is a quick summary of this talk. In this talk, I've introduced the fabrication process for the nanoforests based on a CMOS compatible process. And also I introduced the properties of the nanoforests, including the broad-hand high absorption and the super high moisture absorption. Based on these properties, I also introduced the nanoforests are also integrated in 2 different types of MEMS sensors to improve their performance. So I'd like to thank my group mates for their support and the organization for their support with projects and the funding. Thank you.
Thank you very much for your nice presentation. The nanoforest is amazing, and you show a very complete application from the commercial scenarios. So thank you very much again, and please take care. Maybe we leave the Q&A session at the end. So
okay. I will stop sharing. Okay.
Yeah. Okay. So, please allow me to introduce our second speaker. So, Dr. Rajeev Gupta is an associate professor of material science and engineering at North Carolina State University. Rajeev received his bachelor degree in materials and metallurgical engineering from Indian Institute of Technology, Kanpur, India, and a PhD in materials engineering from Monash University, Australia. Prior to joining the NC State University faculty, he was an assistant professor of chemical, biomedical, and corrosion engineering at the University of Akron, Ohio. He's an associate editor of the Journal of the Electrochemical Society. Rajeev has authored over 130 publications and holds 2 patents. Rajeev's primary research interests lie in the broad area of corrosion and material engineering. His research group focuses on the understanding the structure, processing, property, performance relationship in metallic materials, high temperature corrosion, passivity, corrosion initiation and propagation mechanism, and surface electrochemistry using state-of-art material characterization and electrochemical techniques. The fundamental research is intended to be applied in developing new materials, corrosion characterization techniques, material processing technologies, and life prediction method. So welcome again, and the stage is yours.
Thank you. Thank you so much for the introduction, and thank you so much for the invitation. So today I will talk about some of the research we've been doing from past almost 7 years. So we started the work at University of Akron and carrying out its lightweight, high strength, corrosion resistant, and recyclable metallic materials. So there's a lot of stuff and kind of focus being kind of improving the corrosion resistance and going towards more sustainable future. So first thing let's do is I'll introduce what corrosion is. All of us, I think, know what corrosion is. So when we started using the metallic materials, I guess since then we encountered the corrosion, right? So we're using different metals, we use different alloys, right? And all these are extracted from the ores. And ores is more thermodynamically stable state. So all these metals, once they go back to their thermodynamically stable state, which is ore or their oxides or chlorides or other compounds. And you can see some of the examples. Just I got some pictures here just to show how the corrosion could be, and we see that in our daily life. Now, question comes is like, if you see that, if so prevalent, what we did about the corrosion and how important, how that affects our daily life, right? So just to put that in the perspective, I'm just showing some numbers here. So the cost of the corrosion was estimated in 2016. That was $2.5 trillion. That's equivalent to 3.5% of the GDP. And what is really interesting to notice is that in 1949, Ulick from MIT, he tried to estimate that cost of the corrosion, and that was 2.5% of GDP. So we see that with the time, we didn't solve the problem. With the technological advancement, the problem has even become worse. And when we're calculating the cost of the corrosion, we're not including a lot of factors, which could be environmental impacts and certain kind of important aspects like loss of reputation for the companies and so on. So corrosion being like in all wide range of the in industries, right? So putting that, I mean, I think what is really important to sit down and see what we know about corrosion. If that's a so important problem, what we did so far and what we have to do where the future holds, right? So when we look at the corrosion, I mean, I guess research started long back. I mean, we have like a good history of 70, 80 years of the research. And we developed really tremendous understanding. We have lots of tools and we develop good understanding of corrosion, but still it's not enough. Really fundamental understanding of corrosion at like really atomic scale, that's not needed. Say one example is if you ask me or other corrosion people, like what would be the life of a certain component using or a material in service condition, we would probably ask a lot of questions. It's really hard to predict the corrosion or kind of really hard to have a predictive tool, right? And I think we could do that by using more kind of predictive modeling, developing more understanding of the corrosion mechanism. So that's one area we really need to work on. And most of the time when it comes to the corrosion control, we use corrosion resistant materials. And that's another challenge. We have only limited amount of the corrosion resistant materials. When engineers go to choose the materials, they look at the mechanical properties or other properties, and then we think about the corrosion later on. So our choice of the material is really limited. And I think one of the biggest challenge is, and something we need to work on in future is, if you look at a number of groups working on corrosion, they're not a lot. And if you look at the funding, the part of the funding going for corrosion research, that's limited. So I think there is really need to work on those. So that mostly becomes for the kind of the cost of the corrosion. And then if you look at the current issues of, say, global warming or kind of issue of decarbonization of the manufacturing, reducing the carbon emission, and let's see how the corrosion plays an important role. So what I'm trying to do is, before coming to the like main talk of technical talk of aluminum alloy, just kind of trying to give you a broad perspective of how important the corrosion could be. So if you look at the, say, fuel efficiency, so now we're trying to have the electric vehicles, we're trying to increase the fuel efficiency of the vehicle. So that's where we need the light metals or high strength materials. But now if you look at the corrosion resistant materials, they are not light. Most of them, like we look at stainless steel, we look at superalloys, they are not really light metals, right? Another thing comes is really important for the sustainable future is recycling and reusing. So let's take an example of aluminum alloys. I mean, we have lots of aluminum in the aircrafts, and now question comes once the aircrafts are not in service, can we really recycle that aluminum and make the aircraft again? And question comes, and answer comes, we cannot actually do that. We cannot just recycle and make the aircrafts again, because during that recycling process, aluminum picks up a small amount of impurities. That could be iron, and that's really bad for the corrosion. So can we do something about recycling and reusing? It seems simple, like recycling aluminum and so on. It seems simple, but not really. It's not that simple. And corrosion plays very important roles there. Another way for sustainable future is decreasing the material consumption. And one way is kind of once we're making our engineering components, decreasing the amount of the material we need for that, for the same level of performance. And that could be achieved from high strength to weight ratio. And these materials should have like enough corrosion resistance for given service conditions. We need to decrease the need to produce material, reduce the material consumption and produce less material. And how could we do that? Probably increasing the service life. And the corrosion again plays very, very important role in all that. So the material which are kind of, I just listed a bunch of the properties here: lightweight, high strength, huge compositional tolerance, and that comes kind of helps in recycling, damage tolerance, corrosion resistance, manufacturability, low cost. All these properties we really need in the materials to kind of have the better future. Now let's have a look on our what options we have available. So if you look at the main alloys we have available, our main kind of principal elements we use to make alloys, and that's where we have like nickel, iron, titanium, aluminum, and magnesium based alloys. Copper in there too. So all these, you see that aluminum is 2.7 gram per centimeter cube. In other materials, like if you look at iron-based materials, they have 7.87. So aluminum is promising material. It is lightweight, and it could be used for a lot of structural application as a light material. But if you take pure aluminum, so pure aluminum is pretty corrosion resistant, right? But the problem is that very soft. If you want to use it in any engineering application, its yield strength goes around 25 to 50 megapascal for pure aluminum. So it kind of becomes not very useful for lots of structural applications. So what people did is we developed a whole range of aluminum alloys. So we categorize them in main 7 series of alloys. And then we kind of categorize them age hardenable, non-age hardenable, and that's kind of the way we get the strength in the material. So some of them, like if you look at 2000 series here, 6000 and 7000 series, they have pretty good tensile strength, like 170 to 520 megapascal for 2000. If you see 7000 series, they go up to like 620 written here, they go to maybe go to 650, 660 megapascal of the yield strength. Now we can make the materials, we can increase the strength, but the way we increase the strength by introducing other kind of the phases there, we call them precipitates, and let's see how they impact the corrosion properties. So here is another way kind of schematic. If you look at in this figure here, this shows you different microstructures. So one in the far left here, if you can see the cursor, one in the far left is kind of represents pure ultra pure aluminum, right? And then if I go towards the right, that kind of represents if you start having impurities. So if I have a small amount of iron, silicon impurity present, which are always present in the commercial alloys, right? So they form the coarse intermetallics. We call them constituent particles. They could be few microns, like could be 10, 20, 30 micron big. And they cause huge corrosion issues. Now, if you look at far right hand, that's kind of one schematic representation of precipitation hardened alloy. You can say 7000 series alloys, which has very high strength. If I go from left to right, I'm increasing my strength from say 50 megapascal to 600 megapascal. But how we are achieving that? We're increasing these lots of, you can see these blue particles, a lot of these blue particles, we call them precipitates, and they give the precipitation hardening. So they give the strength, but at the same time, they have very different electrochemical properties than what aluminum has. And they cause a lot of corrosion. So all the corrosion would be around them, or they would be causing, they would either cause a matrix corrode or they corrode by themselves. So the corrosion rate increases a lot as we're trying to increase the strength. Now, if we compare kind of strength and corrosion together with, and what I try to do here is on the y-axis, you'll see the corrosion resistance, and on the x-axis, you'll see the strength, right? So strength kind of yield strength, and corrosion resistance, what I'm saying that, I mean, the way trying to put the data is trying to put the pitting potential or kind of pitting corrosion resistance. Again, corrosion could be very broader terms, but trying to put just the pitting potential here. And what you see here, as you're increasing the strength, your corrosion resistance decreases, localized corrosion resistance decreases in the alloys quite a lot. So I'm at 7,000 series alloys, which you use in aircraft, or 2,000 series alloys, which you use in aircraft. Their corrosion resistance is really poor. So we really need to use lots of coatings and so on. Now, if I want to make something which is really high strength and corrosion resistance, that's the target being somewhere in the top right corner, can we really do that or not with these alloys, right? So in order to do that, what we started thinking about, let's have a look on a stainless steel. Stainless steel is iron and chromium, right? And iron is not that corrosion resistant, and chromium forms chromium oxide and really corrosion resistance. Can we do similar thing here? Can we make, say, aluminum chromium, aluminum vanadium, aluminum moly, something like that? I mean, put corrosion resistant elements and make a supersaturated solid solution. And then you look at the this property space here. We assume that corrosion resistance could be from high solid solution. If you have something like iron chromium solid solution, same way if you have aluminum chromium, right? So that's a simple analogy. And then strength you can get from grain refinement and solid solution strengthening. And the question comes, can we really make those alloys, right? And again, good, like really high strength, like a strength of like 1 gigapascal, and corrosion resistance is similar to stainless steel. Can we really do that? Now, the main challenge comes if you start looking at the phase diagram. Solubility of most of the corrosion resistant elements in aluminum is very limited. So what we did was we actually put whole periodic table and started looking at, okay, all these different alloys and their solid solubility in aluminum, right? So we color coded the periodic table, and if you look at it, SS is the slightly soluble. We're saying anything more than 1 weight percent is soluble, and unsoluble unknown, right? So you see the white ones here, these are the one we say more than 1 weight percent soluble, right? And our interesting alloying elements which could actually improve the corrosion resistance, say chromium, moly, these the corrosion resistant one, you see they are really their solubility is very less, and these solubility are the maximum. Say if I take, for example, vanadium here, right? The room temperature solubility of vanadium in aluminum would be 10 to the power minus 7 atomic percent, that order. The maximum could be 0.4, right? So that becomes like biggest challenge if we want to use them. The solubility is very low. So here we kind of demonstrated, we made some of the alloys here. So I'm just showing here one example of these 4 alloys we made by the casting. And if you made them by casting, what you get is you have the matrix and you form lots of these intermetallics here. So this is the aluminum chromium. So these are aluminum chromium intermetallics. And once you form these big intermetallics, what would happen is they would cause corrosion of all your matrix. So they're kind of not useful. So now question comes, can we make these materials in the form of supersaturated solid solution? And then we looked into the techniques, and there are a wide range of techniques which can produce non-equilibrium alloys, right? You produce microstructure which is far from equilibrium. So one of the techniques could be the ball milling. So what we do is we take a kind of jar and we put some of the ball bearings, we put the powders like here, say we're putting aluminum and chromium powder together with, and then we just seal that in the glove box in high purity argon atmosphere. And later on, actually, we learned that you really don't need high purity atmosphere to get good properties. Even just oxygen or air, dry air environment could be pretty good and could give a better corrosion resistance. But anyway, I mean, just to keep it simple, we try to control the atmosphere. So it's high purity argon, put in the ball mill. So this is one example of planetary ball mill. And if you are lucky, once you do the ball mill for a certain amount of time, you could get the powder like that. And a lot of time you won't get any powder. You might just get everything kind of stuck to the ball bearings and the jars, right? So if you get that powder, what you could do is you could just cold compact, you could do then sinter it to make the components for or the test coupons. You can do spark plasma sintering. You can use the powder for additive manufacturing. You can do the cold spray and things like that. You can do a wide range of things from this powder. Or I mean, from application point of view, you can use this to make the powder metallurgical components, right? So what we did, what the work I'm showing here, what we did is simply we took the powder, we cold compacted it, and then I'm showing what kind of result we get. So we ball milled this different alloys. So in the beginning, we selected 8 alloys: aluminum, chromium, aluminum, manganese, moly, niobium, silicon, titanium, vanadium, and nickel. And in each cases, we put the 5 atomic percent alloying elements. And now if you look at these SEM images, what you see here, this is 5 atomic percent of the alloying elements, so quite a lot of that. And you don't see like really coarse metallic. So this is 2 micron scale bar, right? So you see most of them are kind of uniformly distributed. Some cases are nickel, vanadium, or titanium. You don't see a lot of particles. In chromium, manganese, you see some particles, but they are really, really refined, right? And we use 20 kV 20 kV accelerating voltage for imaging. So you can see a lot of particles which are in the subsurface levels too, right? So actually there are not a lot of the particles there and they're really fine. Now, if I do that EDEX at any point here, I will see kind of 5 atomic percent of the solute. So that shows that the solute is kind of distributed very well within that interaction volume, right? And now just to kind of compare how they would look like if you make them by casting. So you can compare the chromium here is 250 micron scale bar, right? So we refined the microstructure a lot. Now we took those material and we do kind of more the TM and so on. So that's the way the powder looks like. And this is just one example. We make like wide range of these materials, but just one example how they could look like. So this could be the powder. And this is kind of surface looks like after the cold compaction. So in SEM, you see only a few bright particles. And once we do EDEX analysis, we see some kind of iron contamination, some unalloyed particles or some intermetallics there, really fine. And we take that material in the TM. So initially, when we did the work and we got good properties, we thought that most of the alloying elements been in the solid solution. But now, once we look at the TM, we see that it's really, I mean, there's of course lots of, say, this is one example for aluminum vanadium material. So lots of vanadium is in the solid solution, but we also see a lot of other phases. We see lots of heterogeneities in the microstructure. So we kind of characterize that pretty well. I guess probably I won't talk about all those individual details, but if we look into the kind of summarize the kind of the microstructure we get really heterogeneous microstructure, right? If you look at the grain size, that's really few like tens of nanometer, 10, 20, 30 nanometers, definitely stays below 30 nanometers. And depending on the alloying element, we can get different kind of solubilities. So here, what you see is the grain size and atomic percent in the solid solution for these 8 alloys we made. So if I look at the solid solubility, you see that some of the material like moly, chromium, niobium, they're showing more than 3 atomic percent of the solute going the solid solution. So really high solid solubility, right? And just to compare, like if you look at the vanadium, here is a solid solubility is 10 to the power minus 7 atomic percent. That's what it should be. And now we're getting 3 atomic percent. So we are really far from equilibrium. These materials showing really high solid solubility, although inhomogeneous microstructure, right? Now, if you start looking at the properties, what I'm showing here is, this is a bar chart. We're showing the pitting potential and the repressivation potential of all these different alloys. So we did testing in the wide range of electrolytes. We had 0.01 molar sodium chloride or 1 molar sodium chloride. And this pitting potential and transition potential or repressivation potential tells you how corrosion resistant those materials are. You want these numbers to be as high as possible. So now you see that pure aluminum is somewhere here, right? Around minus 600 millivolt, right? So we have 2 pure aluminum here. One is the ball mill, one is the commercially pure aluminum, and pretty close by. So it seems like the grain refinement kind of didn't play as big role during the processing, right? And the major changes are coming from the change in the microstructures due to those alloying elements, right? So like moly or vanadium were kind of very high pitting potential, very high repressivation potential, right? So like minus 100 millivolts minus 100 millivolts or minus 50 millivolts pitting potentials versus minus 600 millivolt pitting potential. There's a huge increase in the corrosion resistance. And just to give you another way to look into the corrosion resistance, what we did was we took all these different alloys, right, and we put in the 0.01 molar sodium chloride for 6 months. And you are taking these samples out at regular time periods and look at what's the size of the pits, what's the number of the pits, what's the pit depth, maximum pit depth, average pit depth. So what we're doing is we're plotting average pit depth as a function of time. If I look at after 6 months of the immersion, all these ball mill materials are here. Like pits didn't grow really much. This is pure aluminum. All the alloys are somewhere here. It is less than 2 micron or 2.5 microns of the pit depth. Now, if I take the corrosion resistant aluminum alloys, I'm not talking about high strength like 70, 75. If taking the corrosion resistant aluminum alloys, their pit size is really high, like 25 micron. So we see huge improvement in the pitting corrosion resistance. Now, we started talking about strength and corrosion, right? If you remember the initial graph where we're putting the corrosion resistance of the pitting potential as a function of strength, here we plotted the Vickers hardness. Commercial alloys lie somewhere here in this region here. We see that pure aluminum has good corrosion resistance, but very low hardness, right? 7075 T651 has the lowest pitting potential, highest hardness. And now the alloys we're making are somewhere here, really high hardness or easy strength and really high pitting potential. So it seems like we can get good corrosion resistance and good strength in these materials by controlling the microstructure, right? Now I'm talking about one more alloy here, and then we talk a little bit about the mechanisms too. So one important alloy is aluminum iron, and if you remember in the beginning, I told you that recycling is kind of a big issue because iron uptake. So you have some amount of iron present in aluminum alloys, and corrosion resistance decreases, right? So we really control iron content. And here what I'm presenting is 5 atomic percent iron, right? Huge amount of iron present in aluminum. We did the ball mill and we got good solid solubility of iron and kind of pretty unique microstructure. Iron was kind of very well distributed in the matrix. And now if you look at the pitting potential, is comparable with other alloys we made. It's very high corrosion resistance, even though with the iron, and high hardness. So it seems like if we doing this, we're changing the microstructure by ball milling or other mean, we can achieve really high strength and corrosion resistance in these aluminum alloys. I'm giving one more example before moving to mechanism side. This example is kind of how we can use these powders. Just one example, there could be several other examples. How can we use these powders in making kind of using in the real life scenarios? So this is one example. I'm showing you the potential dynamic polarization graph for 2024, one of the aluminum alloys, which is the red, and the blue one is the cold sprayed. So we took the substrate and we just cold sprayed with one of these powders we made. And we see huge improvement in the pitting potential. So this is the pitting potential number. This is like really huge increase in the pitting potential number. So by these coatings, you can get really high corrosion resistance. And I think there's nothing new if you say like, well, high corrosion resistance, we can get that by say coating aluminum by chromium or nickel or something like that, right? But one advantage here is that the corrosion potential of these alloys could be a lot lower than what you get in 2024. What does that mean is if the coatings breaks down, these materials could be a sacrificial coatings. They could corrode very slowly and prevents your substrate. If I'm using nickel or chromium or those corrosion resistant material for the coating, the problem is they would make the substrate corrode, which we never want that, right? We want to protect our substrate, not the coating. So they could be really useful material in that sense. And there could be a lot of other applications. Now, coming to understanding corrosion mechanisms, so we got really good properties, and these are kind of the properties I've shown you. They are like not really any optimized properties. You could really do a lot of work, and you can really get even better properties, combination of good properties. But I think really important is to develop fundamental understanding why we get why we get those properties, right? So we did a lot of electrochemical tests. We did. I'm not showing all the work. It's kind of past 7 years we've been working on these materials, right? So we did lots of EIS, long-term EIS tests, like for month-long EIS tests, and we're looking at how the passive film characteristics or surface film characteristics change, how the pits grow and things like that. So one thing we learned is from the EIS data that the passive film more or less remain kind of similar in all these different alloys. One key contributing factor was the charge transfer resistance. What that tells is that your repassivation is kind of changes, repassivation tendency increases with the time, right? And then we did a lot of surface characterization technique like X-ray photoelectron spectroscopy, secondary ion mass spectrometry to characterize the surface film and kind of test our hypothesis and some electron microscopy. So I'll show you some of the results coming from the electron microscopy. So with XPS and SIMS, we can get a lot of good information, but what we really lack is what we don't really know how the pits are growing and things like that. So we really limited with the lateral resolution. But all these combination of techniques give us a lot of new information. So what we did is we kind of took these samples and we performed different electrochemical tests or immersion tests depending on what we wanted to do, right? So after those corrosion tests, we take the sample. So this is one example on the top leftmost, and we kind of deposit platinum and basically make use the focus ion beam to make a TM sample out of it. And main purpose is kind of look at the passive film and the metal interface and characterize how that passive film or surface films look like, or how the pits look like, right? So I'll just show you, I still have some time, I guess. So I'll show you just quick 2 examples here. So this is one example for aluminum vanadium alloys, and we did this analysis for a wide range of alloys. This is a TM image. And what it shows you, if I'm looking at the left one, aluminum 5 vanadium air bond. So in this case, we didn't do any sample, any special corrosion testing. What we did is we took the sample, we polished it. After polishing, we stored in the glove box, and then we took it to the FIV, prepared the FIV sample, and look at the surface film that was formed just in the air, right? So we see like 5.3 nanometer thick film. If I immerse it for 2 hours in aluminum vanadium, the one you see in the right, the passive film grown a little bit. It's from 5.3, it becomes 7.1. And now if you start characterizing the passive film, how it looks like, what we find is, and this is very specific example for aluminum 5 vanadium alloy. And what we start seeing that actually the top layer, you see the EDEX area maps on the right. So we have aluminum, vanadium, oxygen and vanadium together, and oxygen. So looking at oxygen, we understand that would be some kind of oxide there or hydroxide there, right? And you see that the top layer is kind of enriched with aluminum. So it's primarily aluminum oxide. And we did lots of XPS and SIMS, and there's also kind of indicate that the outermost layer is aluminum oxide. And underneath that, we get like really vanadium enrichment. And in between, we think there is aluminum vanadium mixed oxide. So you have aluminum oxide, aluminum vanadium mixed oxide, and vanadium oxide. And when we were putting our hypothesis in the beginning, we thought like, say, aluminum chromium, iron chromium example, is a chromium oxide passive film. We thought in aluminum chromium, you could do the similar thing. Aluminum oxide could dissolve and you can be left with the chromium oxide. But in all these cases, the outermost layer is coming aluminum oxide. It's just that the solutes are getting enriched, right? So that's one important observation we had. Then the second image is pretty important one, and this shows a pit. So you see this image here, right? One on the leftmost, and the corroded area, what you see is like a small pit. It's like 500 nanometers approximately in kind of the diameter. So you see that pit, and then we analyze that pit under TM. And what we really observed was, we look at the EDEX area maps. You see some iron particle there, and we see that this iron coming from the abrasion, from the processing, and that is a cathodic particle and causes corrosion. And now we see that the vanadium and iron are the same spot. Basically, vanadium is depositing on iron. So based on that, we put our hypothesis that, well, in case of the pitting corrosion, I mean, the pit growth or repassivation, there are 2 competing mechanisms, right? So pit can repassivate if you don't have the critical pit solution. And the way we form the critical pit solution is that we dissolve a lot of matrix, a lot of aluminum that hydrolyzes and form really aggressive low pH solution. And here we have the vanadium present, which can deposit on the iron and decreases cathodic efficiency. So that would kind of slow down the anodic reaction, and we never have that critical pit solution. We cannot sustain the critical pit solution and be repassivate. So anyway, those things kind of gives us a pretty good idea about the mechanisms. I'm not talking about all of them, but there's a really good fundamental science there. So we put a bunch of proposed mechanisms for like how this particular materials gives that high corrosion resistance, which we get. And one way kind of comes with the kind of just the passive film, how the passive film could change, and then becomes very important is the repassivation tendency, right? And yeah, and then the last one I would mention is the very important mechanisms we think we still have to validate. We think that those cathodic particles in the conventional materials and in the ball mill materials, they would be very different, and they can change all the cathodic reactions in the chemistry inside the pit. So in summary, I would like to say that, well, there's a lot of science going on there, and we have a lot more research to do to understand the corrosion mechanisms. But this the synthesis of this aluminum alloys with ultra high strength and corrosion resistance is possible, and we just need to control the microstructure and the microstructure and the composition. And in the end, I would like to thank you, all my PhD students. I think given the time, I will not introduce all of them, and NSF for the funding this work. And thank you so much.
Okay, all right. Thank you very much for the wonderful talk, and it's very inspiring. And similarly, we will leave the Q&A session at the end. And okay, please allow me to introduce our third speaker, Dr. Ying Zhu. Dr. Ying Zhu completed her bachelor degree in material science and engineering at Huazhong University of Science and Technology in 2009. She worked as a research assistant at Suzhou Institute of Nanotech and Bionetics during 2009-2010. She completed her PhD in 2015 in Australia's top biosensor and biodevice group, led by Professor Justin Gooding at UNSW. Dr. Zhu's subsequent postdoc work at Dartmouth College extended her biosensor expertise to translational cancer research. Dr. Zhu was supported by Cancer Institute NSW Early Career Fellowship during 2017 to 2020 to establish further her work in using biosensors for cancer diagnosis. She's now a lecturer in the School of Biomedical Engineering at the University of Technology, Sydney, with a continuing position. Dr. Zhu was awarded the Chinese Government Award for Outstanding Student Award in 2014 and the Rising Star Award from Australian Association of Chinese Biomedical Scientists in 2018. Dr. Zhu's current research focuses on developing new nanomaterials and nanoscale devices to capture and analyze biomarkers for cancer diagnosis. She works in multidisciplinary field across chemistry, materials, nanotechnology, and biomedicine. Dr. Zhu has published over 28 journal papers and one book chapter, and presented at 17 national and international conferences. Her works has been cited over 800 times with H index of 16. So, Dr. Zhu, welcome and looking forward to your talk.
Thank you very much for the nice introduction. It was my great honor to be here to introduce some of our work that we've been working to develop optical strategies for the detection of single extracellular vesicle that we want to use for early cancer diagnosis. First, I want to introduce a little bit about my school, University of Technology, Sydney. You probably know in Australia, the group 8 universities. And actually, our university, UTS, is ranked 9th in Australia. And in the recent QS world ranking, we're actually increased to ranked 90th in the world. And we are top of the young universities in the world, ranked 11th in the QS ranking, and also 9th in the TAH Young University ranking. And our university actually located in the heart of Sydney. So here is our university, and next to it is the central station, just next to it. And also the locations such as the Chinatown and also Sydney Tower are not far away. And you can see the beautiful seas and just right closer to it. And here are some images of our campus and also our facilities for research and learning. And we are a technology-focused university, so our aim is to develop technology innovations that can produce impactful research outcome that can improve our society, planet, and professions. And I'm leading a group that I call ourselves a laboratory of in vitro diagnostics, in which we are using either synthetic or biological nanomaterials to improve the performance of in vitro diagnostics, especially for cancers. And here we have several research activities. For example, we are using optical metal surfaces that with the nanostructure for the purpose of biosensing and also bioimaging. We are also using like new biointerfaces for improve the analytical performance of our the assays that we've been developing. And instead of the traditional bioassay, we are developing highly sensitive and also mainly digital format of bioassays for the detection of the biological species. And for cancer specifically, we're also looking into new biomarkers to improve the clinical performance, such as the circulating tumor cells and also extracellular vesicles that I'm going to introduce today. And a big field that we've been working on is called liquid biopsy. So in cancer, the tissue biopsy is the standard way to diagnose the cancer and manage cancer. But tissue biopsy is very invasive, and also it's not suitable for frequent monitoring. And the liquid biopsy, from the name, you can see that it's actually using more accessible biological fluids, such as blood, urine, and also saliva, and to analyze those biological fluids to get the molecular information about cancer so as to reduce the invasive tissue biopsy. And in liquid biopsy, there are different types of biomarkers that people are interested in. Circulating tumor cells are the first type of circulating biomarkers for liquid biopsy, and there are also like circulating tumor DNAs, and these two are being showed very promising in clinical practice. And in our research, we are especially interested in one type of nanoparticle that is with the lipid bilayer that is released from the cells and into the circulation. And we call those extracellular vesicles, and they are used to know as exosome or microvesicles. And those vesicles has been used a lot in liquid biopsy in different clinical applications. And for us, we are especially interested in using these EVs for early detection of cancer. This is because for some type of cancer, such as pancreatic cancer that we are currently working on, detecting the cancer in this early stage can improve the survival rate dramatically. Compared with the other type of biomarker, EVs has its unique advantages for early detection. First, EVs are one of the earliest arising biomarkers from the cancer cells. And secondly, they can contain multiple types of cargoes, such as proteins on their surface, and also proteins and nucleic acid inside them. So by a multi-parameter analysis of those cargoes can use to indicate of tissue of origin. And also, circulating tumor DNAs rely on tumor cell death. However, our EVs, they are continuously shed by dividing tumor cells. So that means they can provide more dynamic information about the development of the cancer. And although EVs has been used a lot in different clinical applications, such as diagnosis, prognosis, and treatment monitoring, their application for early cancer diagnosis are actually quite limited. This is because in the early stage of cancer, the concentrations of EVs in circulation is actually very low. And here shows a model that developed by Weslider's group from Harvard Medical School, showing that the relationship between tumor volume and also the tumor-derived EVs in circulation. And it shows in order to detect the tumor when it's still very small, it needs highly sensitive technology to detect the low concentration of the EVs in the circulation. And however, unfortunately, current conventional bioassays such as Western blotting and ELISA do not have those sensitivity to detect the low amount of EVs in the circulation when the tumor is still very small. And in addition, this about the top one is a the model that's usually used in the EV community, showing they contain like abundant and well-defined proteins. However, Weslider's group shows that a new model that EVs actually contains very rare tumor-specific proteins, and also their cargoes are very heterogeneity. And due to this low concentration and also EV heterogeneity, it seems that in order to use these EVs for early cancer diagnosis, we have to develop highly sensitive technologies that can detect the EVs at a single EV level. And in our lab, we are actually working towards this goal. We are developing several types of single EV detection technology that mainly are using the optical platforms. For example, we are looking at super resolution microscopy that I'm going to talk about today. And also we are using like nanoscale flow cytometry and also fluorescence nanoparticle tracking analysis. Those are like platform that can look at EVs at a single EV level and with a high throughput. And the first example that I'm going to share with you is our technology for single EV quantification that we use new labels based on upconversion nanoparticle. And this work is performed by Dr. Guan Huang. She graduated from UTS, and now she is a postdoc researcher at Harvard Medical School. An upconversion nanoparticle is a type of luminescence nanoparticle. And the unique feature of them is that they can be excited in the longer wavelengths while have emission in the shorter wavelengths. So this is the opposite way compared with other like typical fluorescence probes. And based on this unique emission and excitation mechanism, these nanoparticles are highly suitable for single EV analysis. Firstly, they are very stable, so they don't have bleaching or blinking like the other fluorescence dyes. And secondly, they are very bright and also have sharp emission bandwidth, which means they can avoid like cross interference from different fluorescence probes. And also, because they can excite it in the near infrared range, they can get rid of like the autofluorescence from biological molecules, and so as to increase the signal to noise ratio. And in our research, we are using these conventional nanoparticles as a new type of labeling, and we form this kind of sandwich immunoassay and creates a digital EV quantification. So how it works is that we have a substrate, and in the substrate there is a capture antibody, and this capture antibody specifically binds to the proteins that on the surface of the EVs. And then there's a detection antibody that binds to the upconversion nanoparticles. And instead of using like averaged assembled signals like ELISA, we are performing this like imaging-based and a digital counting of the bright spots to quantify the labeled EVs. And before we do the EV analysis, we have been investigated different like isolation platforms that to isolate EVs from human plasma sample. And here is the comparison of different isolation technology. And here shows the cryo-EM, which with the typical EV structures from the samples that isolated by different isolation techniques, and nanoparticle tracking analysis, which is the typically used EV quantification method, showing that our samples are in the range of small EVs. And also the Western blotting also shows our samples contains commonly used EV markers such as CD81 and TSG101. And also we can compare the quality of the EVs isolated from the human plasma, including the yield and the purity. And this gives us very good information, like what kind of isolation method that we need for the downstream analysis. And after the EV isolation, we're developing our digital detection platform. We show here the analytical performance of our digital assay. So here we use the two different type of EV subpopulation. One is AbCam positive and one is AbCam negative to show the analytical selectivity of our assay. So here it shows that when we incubated with the AbCam positive EVs, there are bright spots showing in the image, and also the number of spots increase with the increased incubation concentration. Well, when we incubate with AbCam negative EVs and to detect AbCam, there are negligible signals, which means our assay is very selective. And we also investigated the analytical sensitivity of our assay. And it shows that compared with the standard ELISA, our assay can achieve nearly 3 orders of magnitude lower of the limit of detection than that of ELISA. And we also validate our assay using the plasma sample from preclinical mouse model, and one is with confirmed no metastasis, and one is with high metastasis. And it shows that from the plasma sample from this mouse, we can differentiate between these two models very, very well. So currently, we are working towards using patient sample that we collected from pancreatic cancer patient to use our platform for the cancer diagnosis. And in our next work, we would like to further increase the resolution of our imaging system. So here we use a super resolution imaging system that is based on STAT. So how it works is that when the EVs is labeled with the upconversion nanoparticle, and we excite the EVs with a donor-shaped excitation beam, and then it will form a donor-shaped emission pattern. And in the center, there is a dip where the nanoparticle sits. And by increase the power of the excitation, the dip the size of the dip will become smaller and smaller, so to further increase the resolution of our image. So here shows an example of the EVs that's labeled with the unconventional nanoparticle, and with our super resolution imaging system, the resolution is dramatically improved compared with conventional confocal. And we also perform like co-localization of two markers that's on one single EV. And this shows the multiplex capability of our assay. And the next example, I want to move away from the unconventional nanoparticle to another type of nanomaterials that is based on plasmonic metal surface, and we use them for biosensing and imaging. And this work is mainly performed by my PhD student, Anthony. And I think the first speaker has introduced about sensor a little bit. And what we have been working on is biosensors. So biosensors means that this type of sensor can be used for the detection and quantification of biological species. So how it works is that there is a interface that is with a recognition element, and this recognition element can specifically bind to the analyte of interest in like within a mixture of like different type of interference. And when this specific binding happens, there will be a change that's on the transducer. And we are currently working on the sensor that has the optical change. So that is the optical biosensor. And I believe the most well-known optical biosensor is surface plasma resonance, and which the first speaker also introduced a little bit. So how it works is that when the light is illuminated on this sensor surface, it will show unique optical features. And when there are materials that binds to the sensor surface, there will be a red shift on this optical spectrum. And by monitoring the shift of this peak, we can perform this real-time monitoring and quantification of of the biological targets that bind to the surface, and also get kinetics information from them. And in our research, instead of using the gold film that's used for standard surface plasma resonance, we are fabricated these plasmonic nanostructures. For example, we can fabricate these nanohull rays that's produced by well-established nanofabrication. And this nanohull arrays shows a very distinct optical spectrum. And when there are material that's deposited on the surface, the peak will have a red shift. And by monitoring this, the position of this red shift, we can perform this like real-time monitoring. And this shows an example of the detection of another cancer biomarker, prostate-specific antigen. And because these nanoplasmonic chips has like unique colors, and we are also working towards using the color change for sensing purpose. And here shows that when we deposit materials on the surface, the color will change gradually, and we can even quantify this change by getting the pixel values in both red and green channels. And it shows that the pixel value actually has a linear relationship with the polymer thickness that deposited on the surface. And while we are working on using the plasmonic substrate for sensing purposes, we also looking into how we can combine this plasmonic structure with the super resolution imaging. So this can be achieved by one certain super resolution imaging that is called a structured illumination microscopy, shorted as SIMS. So STEAM has a unique feature that it has a good combination of the resolution and imaging speed and also field of view. So it means it's very useful for high throughput imaging analysis. And how SIM work is that when there is a small particle and illuminated by this illumination pattern, it will create so-called moire fringes. So the high frequency information from this small particle can be extracted by these moire fringes. However, in traditional SIM, because the pattern is created by traditional optics, and so that it is still like diffraction limited. So the resolution of conventional SIM is still not very high. And the beauty of the plasmonic structure is that the plasmonic structure can provide almost arbitrary spatial frequency so as to provide ultra-fine illumination patterns. And here shows a very initial result. This is the interference patterns of the plasmonic nanohull arrays that we fabricated. And this shows like the result of the improvement of the imaging resolution when we use our nanohull arrays and compared with the diffraction limited image. And right now we're working on like using this system for the single EV analysis. So I think this is the end of my talk. So some of the take-home message, I've shown that the extracellular vesicles are highly potential biomarkers for liquid biopsy, especially for early cancer detection that we are currently working on. And in order to use these EVs for the early detection of a cancer, it's very necessary that to develop highly sensitive single EV analysis tools. And we are currently working on several optical platforms, especially on those super resolution microscopy using either the upconversion nanoparticle or the plasmonic assisted structure illumination microscopy. And with that, I would like to thank my students in my group and also my collaborators from University of Technology Sydney, UNSW Sydney, and also Centenary Institute of Cancer. And also, I thank the founding body, Australia Research Council, Cancer Institute, NSW, and PineKind, the Australia Pancreatic Cancer Foundation, for their support. And thank you very much for your attention.
Fantastic talk. Thank you very much for the nice presentation again. So let's move on the next session, which is a panel discussion session. Before start, please allow me to introduce you our two panelists today here. The first one is Dr. Jiushuai Xu. Dr. Xu is currently working as a postdoc researcher and serving as a junior group leader in the MEMS research team at TU Braunschweig. He received his PhD degree with highest honor in the Institute of Semiconductor Technology from TU Braunschweig, Germany in 2020. Prior to that, he received his bachelor and master degree from Northwest A&F University, China, in 2011 and 2015, respectively. His research focused on the semiconductor, micro and nanofabrication, advanced processing, MEMS sensors, and micro-nano detection system. He has published 33 papers in academic journals and conferences, has contributed to the authorship of 3 books. So welcome. And our next panelist is Dr. Jinchi Han from Peking University. Dr. Han is an assistant professor and a Boya Yang scholar in School of Integrated Circuit in Peking University. He received his bachelor degree and a master degree from Tsinghua University in 2013 and 2015, respectively, both in electrical engineering. He received his master degree and a PhD degree from MIT in 2018 and 2021, respectively, both in electrical engineering and computer science. Prior to joining Peking University, he was a postdoc associate in Research Library of Electronics at MIT from 2021 to 2023. 3. His research is focused on the new diagram of active micro nanostructure for application in sensing, actuation, computing, storage, and energy harvesting, aiming to reduce the energy consumption of key components of microsystems and promote their application in the field of Internet of Things, artificial intelligence, wearable electronics, etc. His innovative work on nano electromechanical transducers has received intensive media coverage and attention from the industry. He has published over 20 peer-reviewed articles and invented 5 patents. So welcome all of you, and thank you again for all the speakers from a very different background subject. So let's move on to our discussion. So I think it's better to start from our panelists. We follow the order. So maybe Zhu Shui, you want to start first?
Yes, hello everyone. So thanks to all the very nice talks. Actually, I have a question firstly from Professor Mo. Very good nanoforest work and their advanced application for the respiration detection. It's very good idea also. So I have a question about the selectivity definition, like as you presented, moisture or humidity, temperature, and also the deformation of the flexible substrate. They all have influence on the output of the sensors, nanoforest-based sensors. So how do you define which signal has been induced by the respiration purely?
Okay, thank you for your question. As for the humidity sensors, we have detected the influence of different gases and also the influence of other parameters, including the temperature and also pressure. But we found for the application of humidity detection, the other parameters they are the influence is quite small. So it has little influence on the humidity parameter when it is measured.
So actually, the temperature and the deformation of the substrate, they are ignored. So they're not distinguished in the application.
Yes, that's right.
Okay. Thank you.
So maybe, Ying Zhu, you have any question for any speakers?
Sure. Yeah, first, thank you all for the 3 wonderful talks. Actually, I have questions for like each speaker. So maybe I'll start with Dr. Mao. So actually, I remember you were talking about like the fabrication of the like forest, nanoforest. So it's using like PI photoresist, right?
Yes, that's right. In our experiment, we've tried the different polymers, including photoresist, and even for the photoresist, we also tried the different types of the photoresist. But we found that polyimide is the best one. We can get the structures and we can control the morphologies and the dimensions better when using the polyimide.
Yeah, so basically you mean like this kind of fabrication is not specific to the PI photoresist, but you get the best kind of resolution or like a fabrication control using the PI photoresist. Is that correct?
Yes, that's right.
Okay. So my second question is like I'm just wondering how you can control, the density and also like the size or like maybe the diameter of each pillar in the forest. Is there any like way to just make, to just like control the fabrication process so that you get like an arbitrary like density you want?
That's a very good question. And for us, we cannot control the exact size and the exact structure, just like an array of the nanoforest. But we can control the repeatability of the all the whole as all the structures as a whole, and because in our applications we only use them as an area, a surface in the humidity sensors or the optical sensors. They can be used as a whole. We don't need to control them to be like the array structures.
Okay. Yeah, actually, one last question for you. So, I saw like you were trying to like fabricate different like kind of nanoforest with different material. Is it just using like the PI resist to make the forest and then use it as like kind of soft mask and then do etching or something like that? I mean, I remember you showed some like metal for like a nanoforest and yeah, something like that.
Yes. In for the different types of nanoforest, for the silicon, especially for the silicon nanoforest, we use the etching step to transfer the nanoforest to the silicon substrate. But for the other materials, we usually use the chemical deposition or physical deposition to cover another layer of the or another layer of film on the nanoforest.
Okay, I see. Okay, thank you.
Okay, thank you.
Yeah. Second question is for Dr. Gupta. So actually, yeah, it's very interesting and very important to just like show how the the alloy can, I mean, the corrosion like properties can be improved by using like some kind of like 5% of different kind of metal in the alloy. I'm just wondering whether there's any like drawback of adding that. I remember you were talking about like the two most important metrics. One is the tensile strength, right? The other one is corrosion. So basically, is there any other kind of metric important, especially important to structures? For example, do you also consider like fatigue? For example, like how making those alloys will like influence the fatigue properties of the metal?
Yeah, you're absolutely right. And this like corrosion, and my research been focused on corrosion, so you've seen a lot of stuff on corrosion, right? And the reason I was showing hardness there's quick kind of measure of kind of yield strength. But I mean, that doesn't qualify material for practical applications, right? So, I mean, of course, we need to check out the ductility, right? And fracture becomes very, very important, right? So if we go for the real applications, we have to do a lot more work there. And I mean, there is kind of chances. I believe some of this material could have really good fracture toughness and other properties which are desired. And reason is that, I mean, if you look at the microstructure, right? And what is really fascinating to me, or what I really find most important here is the kind of the microstructure they have. So I haven't shown you a lot of data, but some of the microstructures you will see that you will see like matrix which is really enriched with the solute. It's kind of supersaturated solid solution. And then in between them, there are very small pockets of really soft aluminum, which is not enriched with any of these alloying elements. So most of the time, what happens if you get microstructure like that, you would see really bad corrosion. But now, I mean, this kind of the way this microstructure is kind of you get good corrosion resistance, but these soft faces hopefully would give you a good fracture toughness and things like that. So I think, I mean, we haven't done anything on fracture toughness. We did some very preliminary tensile testing on the small samples, and we saw some really good ductility. Like in one case, so like 15% elongation at failure, which is like really huge for close to a gigapascal of yield strength. So there are lots of possibility. We need to do a lot more work in that sense. And looking at the fracture toughness, stress corrosion cracking, and other forms of corrosion and other failure modes is super important.
Yeah, actually, another like maybe very, I'm not sure. Like I'm not in the field of corrosion, but my question is like when you evaluate corrosion, are you kind of evaluate like how long it's sustained like inside sodium like chloride solvent, or like also or you also evaluate how it is resistant to like other kind of chemicals? I'm just like curious.
That's a very important question, and I guess that's the yeah. So we need to consider environment becomes so important, and we look into the pitting corrosion, the localized corrosion. That's the mainly we looked into, but all these corrosion modes kind of changes when we go from one environment to another. So of course, before we start using them, we have to look at the wide range of the corrosion. For aluminum alloys, localized corrosion, pitting potential becomes like main mode of corrosion. So that's where we started looking at the sodium chloride solution. We looked at some acidic solution and some like really high pH conditions, because we know that aluminum oxide is not stable in low pH and high pH conditions, right? So we're trying to look into those conditions, whether these alloys probably could give really good corrosion resistance. So it seems like they're better than pure aluminum or other aluminum alloys, but still not highly corrosion resistant if you change the pH a lot. So they are more good for the neutral pH. But of course, we have to look into more mode of corrosion.
Okay. Yeah, actually, one last question is like, I was working on some like kind of micro scale actuators, and we use the metal a lot, like as both electrodes and also activating elements. So corrosion is also like something we need to consider if we are not doing like well encapsulation, right? So then I'm wondering, like when we were doing such kind of like metal deposition, we probably use like evaporation or sputtering. So I'm just wondering how we can like leverage like how it is like helpful to our work. For example, whether we can just do co-deposition of like aluminum plus maybe forgot like which kind of metal to just improve the resistance to like corrosion. Is it possible? Like if we do it in the like a micro fabrication fashion?
Yeah, I think we have to look more into the material. Like it's kind of becomes very unique, and the way it is right now, the way the corrosion research is, we have to look into what exactly the system is, what your material is, and what we can put on top of it, right? So there would be a lot of corrosion resistant the kind of coatings you could put in, or you can have kind of the gradient structure. But really need to look into what exactly the material is. But I think that there are possibilities. You could definitely like can just put the surface, which is really corrosion resistant.
Okay, I see. Okay, thank you.
And that's I guess very, I think, easy to control with the say plasma deposition, or with lots of techniques. It's really easy to kind of create those kind of the gradient structures. And aluminum is not kind of the best corrosion resistant element there.
Okay, I see. Because we use like either gold or platinum a lot, like those noble metals, but like aluminum is definitely like something we use a lot. I'm just wondering if we just, when we kind of deposit like aluminum as the electrodes, if we just add a little bit, I'm not sure, like maybe chromium or something inside, like do like a co-deposition, whether we'll have like same kind of improvement in corrosion in a way as you did, like in the kind of like bulk materials.
So if you're doing the vapor deposition or plasma deposition, actually you can get better corrosion resistance than what is shown here. Like if you have aluminum chromium, for example, and there have been some work done in early 90s on the thin films of aluminum. So you can get tremendous improvement. Even not any alloying element, we've seen with the oxygen only. If you can kind of increase the oxygen solubility, you can see huge improvement in corrosion. So just kind of changing maybe your the gases you're using, the chamber gas pressure, you can just aluminum, and you can get or other elements, you can get huge improvement. And you just have to do that surface kind of. But yeah, I'll be happy to talk if you need anything over there. But yeah, there's lots of possibilities with the aluminum in that case. Yeah.
Okay.
Thank you. The properties would depend on the microstructure, how well you control the microstructure. More homogeneous distribution of chromium in the matrix, better the properties you would get, most likely.
Okay, interesting. Thank you very much. Yeah. And I also have questions for, sorry, I have too many questions. Yeah, I also have a question for Dr. Zhu. Yeah, actually, because I work on like the fabrication of nanostructures a lot, I saw like in one of your work, you were using like kind of array of nano holes, right? Nano holes as like plasmonic structure to enhance or like as kind of the sensing medium. So I'm just wondering, like, what is the design criteria of those holes? I mean, I saw like the diameter of the small holes around like 200 nanometers, if I remember correctly. So, and also spacing kind of like similar. So is there any kind of like design considerations for those, like array of the structures?
We are actually using console simulation to predict the optical structures that's from the structures. So I think it's very flexible. So we can like design any sizes and also any pitches, and even like changing like say from the regular array to like hexagon shaped array, and you can kind of control that and then design the optical properties.
So basically, we are looking at this like the kind of the where the peak of the spectrum is, right? And then you just like detect like the redshift of the peak. Okay, I see.
Yes.
So
generally speaking, I think the smaller the holes, it will like blue shift the spectrum of the peak, and also like the shorter the distance will blue shift as well. I think that's generally, yeah.
Okay, I see. So for that kind of like sensor, you were I remember you were using that to like measure the thickness of the film that deposit on the surface, right? So is it possible to do like kind of like is there, for example, like there's only like one small area that kind of deposits some material? Is it possible to do like kind of mapping of where the material is and how thick of the material on each area? Is it possible?
Yes, I think that's possible. So if you want to just define just one certain area, I think you can use say a microfabrication to create those like hot masks around the sensor area. And in terms of say if we want to look at like biological species, we can like confine them say using microarray spotting technology to just spot the analyze into certain area. So that's possible.
Okay. So yeah, I'm also wondering. I was curious. Like for current design, like all the structures are kind of identical, right? Like the nanostructures. So is there any benefit to make them into like a different designs? For example, for some area, those of the like one diameter and one spatial distance, and in another area. I mean, I'm just curious whether it's useful for some application if you design them in a different way. Yeah.
Yeah, I think that's the beauty of the meta surface you can actually control. So different, like I saw those works that with like gradually change the distance, and also there are in optical sensing you can design say the final resonance that is break the symmetric of those structures. So creating different size of the nanostructure, or not making them holes but other like breaking structures as well. So yeah, there's a lot of work that can be explored.
Okay. Another question is about another work about detecting like EV. So you were using like upconversion, like a nanoparticle as kind of the media to just show where the EV is, right? So like how to functionalize the nanoparticle? It needs to be, it needs to kind of like know, to kind of bind to the EV, right? Like in some way.
Yes. So the nanoparticle, so when it's synthesized, it's actually have the carboxyl group, and from those carboxyl surface group, you can build like linkers and then attach to the antibodies. So those we use those antibody attached nanoparticle and then bind to the surface proteins on the EVs.
Okay, I see. So in that case, like I think I'm not sure whether like the question is proper, but if, for example, if there are like two EVs close to each other, like is it possible to like distinguish the two like EVs, or you can just like detect there is like one EV there. I'm not sure like how high the spatial resolution is.
Yeah, so that's actually why we want to develop the super resolution imaging system. So like typically when people say like a single EV analysis, you can't really strictly say they are at a single EV level. It depends on the resolution of the imaging. So some of like the digital spotting may contain like several EVs. So that's why we moving towards like improve the resolution of our imaging system, so that once the resolution improves, we can say that we can look at single EVs or like two EVs close to each other.
I see. Yeah, thank you very much. That's all my questions.
Fantastic.
By the way, I may also have a question for the single EVs detection. So, like single particle, single molecule detections are always interesting topics, but it's also difficult to localize or to select the single particle or to find it and measure it simultaneously. So my question is, how do you localize your single EVs and actuate it, then measure it? I think it's not so easy to achieve.
Yes, so I think in the researching like research labs, many people like developing like single molecule technology. Those has a limitation of low throughput, means that you can't analyze a lot of targets. But in actual clinical translation, you have to like improve the throughput of analysis. So that is why we are particularly interested in those technology that I showed the example. For example, the imaging system and nanoflow cytometry, nanoparticle tracking analysis, they actually can see many particles at the same time. So that is how we want to create like the accuracy, like in terms of diagnostics. Yeah, that's something to consider if one wants to translate their technology into the actual clinical setting. Yeah.
Thank you.
So, all right. Tushar, you have any question for Dr. Gupta? Or
yes. So because this metal corrosion is all new for me. So it's, of course, this we heard a lot. So I heard also about the corrosion happens fastest at the interface between air and liquid. I don't know if it is true or not, and I want to know if Dr. Gupta have also done some research to do the investigation on the at the interface corrosions.
Yeah, that's true. I mean, air-liquid interface becomes pretty important. I mean, a lot of failures, like people kind of, I mean, you look and you think that, well, I mean, you kind of do your investigation, inspection, just where you see there will be most of the corrosion, but forget to look at that interface, right? And then, you have one side, you have more access to oxygen, another side not. So you kind of develop kind of local kind of corrosion chemistries. Now, for these materials, we didn't look into that, and so the reason kind of we were looking just aqueous corrosion, because these are new materials. We're not using them right now for any applications, right? So it's kind of just to assess how good they would be if we put them, say, in marine environment, we submerge them. And I mean, yeah, if we using them, all these issues becomes pretty important. And as you said, the interface between air and the liquid, right? All those, I mean, if the material is kind of corrosion resistant, mostly it would be more corrosion resistant to that type of corrosion too. So we're going with that hard, but that may surprise us, right? Once we do the real testing. But yeah, that's very important issue. Yeah, we didn't look into.
Yeah, maybe an additional question. So, like we talked before, you also travel around to develop this topic. Like from new materials to application, maybe it takes a very long time. So maybe it's also a lot of pressure. You have got a lot of funding. You want to finalize or realize your topic. Maybe you can share also with the other young researchers, how is your experience on dealing with these pressures and this process?
Yeah, I think it becomes like so when I started that the research, like when I joined as assistant professor, so this was like we got like 2 students as to start with. And one of the students, the target was like kind of choose some topic which would be like, I would probably work on that for a long time. And the first thing comes is like you put an hypothesis, which seems crazy and not even sure about whether it would work on or not. So, then the first stage is where your hypothesis is working or not, and it works and you get some funding. So we had kind of quite a bit of funding for the fundamental research. So that's where we try to understand the mechanisms. And I guess now when it comes to the next level for the application, I guess there are different level of challenges now. I mean, you have to find an industry partner or someone who's really interested in really that applied kind of the research. And I think that's where we are. And so I think one good way would be just putting a patent in the beginning, right? And then see who could be interested in. And that's what we did. I've been slow in the patents, but we did a few, and probably you get some funding, and if the research is really good, you keep
Yeah.
working and find a. And one more thing I would say, like once you have a product, I guess you look at the multiple aspects of this where you can use. So for example, I have the powder, and then I'm looking at initially my thought was like kind of replacing steel or stainless steel. And then, I mean, there are whole different level of challenges, right? I mean, there is already well established the techniques and the procedure. So why someone would change to whole new way of making the material, right? So we have to start looking into where it's easy to kind of use this powder. So I was looking more where the people use powder, right? So for
Yeah.
example, for display people use powder, additive manufacturing people using powder, and there is whole this powder metallurgical component. So kind of talking to those industries and if they are interested in. So I guess that's where we are now, kind of the next challenge of where we can find the application of these materials.
Yeah. Thank you for sharing this great work and experience.
Thank you.
Very great. So, and we are quite good on our time. So, I mean, if you have any last question, you can take the chance. Okay, so if no one has more questions, so I'd like to thank all our guests, three speakers and the two panelists again for your participation, and thanks ICANX for providing this platform for us to meet together here, and hope we can keep connection in the future. And thank you all the audience to join us today. In the end, I'd like to thank the speakers specifically. So we prepare like a certificate for the speakers, every speakers here. So the first one is Dr. Haiyang Mao for her wonderful talk, use talk. This time for the micro sensor with Nanoforests. And thanks our next speaker. Let me share my screen. Okay, that's good. Our next speaker, Rajeev Gupta, for his wonderful talk about the lightweight, high-strength corrosion resistance and the recyclable metallic material for sustainable future. And our last speaker, Dr. Ying Zhu's wonderful talk about optical strategy for single extracellular vasculars detection towards early cancer diagnosis. And so in the end, I'd like to also invite all of you on the audience to attend our next youth talk. The main topic, the synthesis, regulation, and application of liquid metal about micro and nano materials. The next youth talk will be in Chinese. So welcome everyone to come again, and wish to see you next time.
Super.
再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can，你也能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越